Okay, so in the last lesson, we investigated rectangular Riemann sums. So, a little recap here. We had functions, and we approximated their area by cutting them up into little rectangles. Right? This is not the best drawing I've ever drawn of Riemann sums, but here it is. So, the problem we ran into, right, is that this approximation is not very accurate, right? So we have these areas between the rectangle and the function in this case that cause our estimation of the area to be either an over or under approximation, right? So these are, again, rectangular Riemann sums. Well, here we are now going to tackle trapezoidal sums. Okay, so the problems are going to look very similar, so we're still going to use a certain number of sub-intervals. We're still going to look at the bounds of integration. So in this case, 10 minus 2 over 4 sub-intervals is going to be 8 over 4 is going to be 2 is the width of each sub-interval. So we're going to cut this integral up into trapezoids of height 2 in this case. Okay. So let's take a look at what that would look like. So I'm going to edit my graph to represent these trapezoidal sums. And then we'll talk about what it means to be a trapezoidal sum. Here we go. So here is our trapezoidal sum for this particular function. So what we will notice, right, is that each corner of the trapezoid is now on the function. And then instead of having this big, we'd have a huge under approximation here. Our under approximation is actually very small. Okay, so both corners are on the function. And then what I could do is I could use the formula for the area of a trapezoid for each individual trapezoid to solve this, or approximate the solution, right? For this lesson, we're not going to do that, however. We're just going to say we're looking at the over versus under approximation factor. And obviously, this is a small under approximation. It no longer matters for these. This is another benefit of these. It no longer matters whether f is an increasing or decreasing function. Okay. So this can be useful when the function is like increasing for part of the interval and decreasing for other parts. However, there is a relationship between the quality of the approximation and concavity. So in this case, this is an under approximation and the function is concave down, meaning it opens downward. So we'll take a look at an example of an over approximation here in the next one. Okay, here is my example of a trapezoidal sum that is an over approximation. So you can take a second and look at my steps here and notice the width of my subinterval is the difference between the bounds over 3 subintervals. Okay. So notice now that we have an over approximation, right? So my graph, the function is a little bit below the edges of my trapezoids. Okay, so this is an over approximation. It's too big of an estimate. And that's because the function is concave up. My previous example was concave down. This example is concave up, and you can see visually the reason that we have an over approximation here versus an under approximation up here. Okay. That's all there is to this lesson. Just you're drawing the subintervals as described and then determining if they're over or under approximations.